All right, so we'll go ahead and get started here. We're going to move on to the next chapter. I was thinking about the exam, the next exam we need to do. My intent was to have all this next stuff about energy and all on that exam, but I don't want you guys to have to worry about it over spring break. I want to give you an actual break. So I think what I'm going to do is give you the exam on Friday, this coming Friday prior to spring break. What I'm going to do is I'm going to cut down the material on the exam. Will just be kind of inclined plane problems, two-dimensional forces, and the uniform circular motion stuff that we just got done talking about. I'm going to make the exam available to you starting Thursday morning, and I'll give you until Sunday at midnight to get it done. I've fixed, I think, the formatting problems with the exam online. I'm going to try to do something a little different with this one. I'm going to include, there will probably be fewer questions, but it will be more heavily relying on your submission stuff. So for example, I'm going to have a couple of questions on there where I'm going to ask you to draw and label free body diagrams and do the equations symbolically. So there's not going to be a lot of place for you on the exam to actually put numbers in and get correct answers out. So it's going to require a little more work from you on paper. But like I said, it's going to be less material and you'll have a little bit longer to do it. So I think that will be fine. That'll get us through our second exam, take us into spring break, and then we'll come back after spring break and spend about 5 or 6 weeks finishing things up. And then we'll do a final exam that will cover whatever we can get to at that point, and we'll be good. So let's go ahead and start on the idea of energy. So I told you that the last time that as we have been doing these problems, we've been looking at two-dimensional motion, we've been looking at uniform circular motion, and we've gotten some pretty complex equations out of this, and we've gotten a lot of vector kind of stuff. And I told you that there's an easier way to do things. Well, we're going to start on the easy way today. The easy way to do things is the energy method. So we need to talk a little bit about energy and what that really means. So the energy in the system is a combination of a lot of different things. There's an equation about energy that you guys have probably encountered at some point, but you don't really understand what it means. It's Einstein's relativity equation, E equals mc squared. So energy is a physical quantity that we typically measure in something called joules. So energy is typically measured in joules. Sometimes you can get measurements of energy in things like calories. You probably heard about this if you looked at nutrition and going to the gym and things like that. You talk about how many calories get burned. That's just a measure of energy. But our SI notation for energy is going to be in joules. Now, E equals mc squared, this is an equation that talks about the relationship between matter and energy. Matter and energy are kind of the same thing. What we have talked about so far generally has been forces. Forces have to do with the expenditure of energy. The total energy in the system is going to be a function of the mass of that system and the speed of light. actually the square of the speed of light, c. This is very, very complicated to derive, and I'm giving you a very, very simplified explanation of it. But I just want you to understand that energy and matter are connected. So energy is in joules. If you care, since mass is in kilograms and the speed of light is in meters per second squared, then we get something that looks like, speed of light is not squared, it's meter per second quantity squared. Important difference. Meter per second squared is acceleration, but this is a velocity, it's squared. So this works out to be something that looks like kilogram meter squared over second squared, which is not a Newton. If we had just done kilogram per meter or kilogram meter per second squared, that would be a Newton. That's a unit of force. This is a unit of energy. So we get this kilogram meter squared per second squared. That's a big weird unit. So much like Newton's, we just come up with a new name for it. It's called the joule. There are lots and lots of ways you can convert joules to something else more interesting. Calories, for example, another unit of energy is the volt in batteries and electrics, electrostatics. You're talking about voltage, electrostatic potential. You get something called power that's related to this that we'll get into. So my point is that we're going to use something called energy, and it's measured in joules. And let's see what that kind of means and how we're going to use it. So let's say that we have our typical car here, and my car has run out of gas. And let's say that it's a mile to the nearest gas station. And the only way I can do this is to push the car to the gas station. So let's think about this scenario. Again, we're going to assume just kind of a flat surface. We're not worried about air resistance, anything like that. We're not even going to complicate it with an incline yet, but we can. So let's just think about what's going on. I'm going to have to push this car. I think that if we all considered this as an activity for going to the gym for your daily or workout or something, that you're probably not all that interested in pushing a 2,000-pound car for a mile. That's a lot of work, right? Now, when I say that means that's a lot of work, I think everybody kind of intrinsically understands what I mean. It's the amount of effort you have to put in. Work is actually a term in physics. Work is related to the amount of energy in a system. In fact, there's something called the work energy theorem. That says the work that is put into a system, or the work that is done by a system, is the opposite of the change in energy. In other words, if we expend energy, right, we put in a certain number of joules, we burn a certain number of calories, we can do an amount of work. So we need to think about what work is. What would make us work harder on this car? Well, work is really going to be a function of how much effort we put into this, right? How much force we apply to the car. If I just barely push on the car, eventually I'm gonna get it to go this mile, right? But it's gonna take me a while. So the work that's done is certainly a function of the force that we apply. But now we think about the next piece of this. If I push this car and I push it just momentarily for a second or two, I'm not going to be that tired. But if I push this car for 10 minutes, for an hour, gonna be tired, right? It's not necessarily the time, though, that we're worried about. It's the distance. So I'm going to assume that I'm applying a certain amount of force, F, to this car. And the longer I keep this car moving, if I'm applying the same amount of force, the more distance I cover, the more calories I have to burn, right? So work is force times distance. There's one other thing that we need to incorporate into this. What if the car is on a hill? Right? Instead of doing just a flat road, what if it's up some kind of hill? Well, then what I need to know is the amount of work I have to do is going to have something to do with this angle. Well, since the amount of work that I have to do is dependent on the distance and the force, it's got to be perpendicular to the force. So in our diagram here, the perpendicular component of the force, if you remember, is just the cosine of that angle. So work is the force times the distance times the cosine of whatever angle you're trying to apply the work over. Now you might be thinking, well, what about the mass of the vehicle? Well, what does the mass of the vehicle matter? If we remember in our two-dimensional motion, let's set up just a simple XY axis. And we have the car at the center. The car has got to have some weight, which is mass times acceleration due to gravity. We're going to have some frictional force working against the car. And we have to apply some force. But we know there's equal and opposite forces. So there's got to be a normal force here. And remember, the normal force is just that coefficient of static friction. Well, sorry. You got this normal force. So what we need to do is really find out what the force due to friction is. Those have to be equal. And we know that the force due to friction is that coefficient of friction mu times the normal force. So what we have to do is find, in order to move this thing, or in order to think about the amount of work that gets done, if we want to consider the mass of the car or the acceleration due to gravity, it's going to be a whole lot harder to do on Jupiter, for example. We need to account for the weight. We've accounted for the weight intrinsically in saying that we are applying enough force to overcome the frictional force. And so our force just has to be mu n. So if we want to come down here, then we can say that work is force times the distance times cosine of the angle. Well, we know the force that we need in this case is mu n. And then whatever distance it is we want to move. And then cos theta of our angle. Now, keep in mind that we're not always going to be on this horizontal plane, so our frictional force is not always going to be mu n. Our frictional force may be defined by something else. But my point is, all the things about the weight of the vehicle and the friction between those surfaces, if you want to start incorporating air resistance and things like that, all that lives inside this force variable. So that force variable really means a lot, right? As we should be seeing now, remember on one of the first days of class, I talked about Newton's laws of motion, and I talked about Newton's second law, and we kind of use this F equals ma thing to represent Newton's second law. But I think I've said before, and I know I say this to my students at Arkansas Governor's School every summer, and when I've taught high school, that Newton's second law is not F equals ma. And if, especially my upper division students, I punch them in the throat if they tell me it's F equals ma, because that's just far too simplistic. And we're starting to see the reason for that now, right? Because force means a lot of things. There's a lot of inherent meaning inside force. So Newton's second law actually talks about proportionalities between acceleration and energy that we have to impart to overcome the inertia. We're going to get into inertia a little bit more when we start talking about collisions here in a couple of weeks. We'll talk about inertia being the tendency of an object at rest or in motion to remain so until acted upon by an outside force, Newton's first law. Notice how all Newton's laws of motion talk about force, and they talk about applying force in different ways. So work is what we're trying to talk about here. Work is the amount of energy that we have to put in order to cause that force, right? So remember, I'll put it up here again because this is important. Work is a change in energy. Energy's in joules. So work should also be in joules, right? Because you have joules to joules. That makes sense. Calories, ergs, whatever unit you want to use for energy, that's going to be your unit for work. In this case, we're going to work with joules. We need to think about, though, what this means. Change in energy. So where does the energy come from? Yeah, you could have giant philosophical and cosmological discussions and go all the way back to the idea of the Big Bang, Yggdrasil in Norse mythology, whatever creation story you want to believe in, you can go all the way back to that for where does energy come from. This is not a philosophy class. I am not a philosopher. So we're not going to have to do that. Where we're going to start is the assumption that there are two kinds of energy. Types of energy. One is going to be potential energy, and one is going to be kinetic energy. So these are the two kind of energies that I'm going to be interested in. Potential energy. Sometimes we talk about this as rest energy. If you want an example of potential energy, think about a time in your academic career where an instructor has said to you, oh, you have a lot of potential. It means you have the ability to go somewhere. So potential energy is kind of stored energy or rest energy. It is what we have available to us in order to do some work. So a lot of potential. Kinetic energy, this is our movement energy. So once something is moving, it requires a certain amount of energy to keep that thing moving. So since there are two kinds of motion or two kinds of energy that we're going to be concerned about, potential and kinetic in this case, our total energy then, E sub T, E total, our total energy must be the sum of potential and kinetic energy. I will use U a lot for potential energy. It's kind of a generic thing, and the reasons for that have to do with classical mechanics. We're trying to make these as general as possible. I'm going to show you the common case we're going to use is gravitational potential energy, but there are many, many, many things that can give something potential energy. Electric potential, for example, thermal potential, chemical potential. These are all kind of different types of potential energy, and they do not all have the same mathematical form for finding them in an equation. So we use the general U for potential, because now this can mean whatever kind of potential I have, right? Our kinetic energy similarly is going to be whatever kind of motion we're talking about. You guys that have had chemistry, you probably talked about something called Brownian motion, which is the motion of molecules in an object, and they kind of generate heat. So there's going to be some kind of thermal energy released from that. That'll be your kinetic or your thermal kinetic energy. In our case, we're going to look at the very, very simple case of just gravitational potential energy. So we need to think about what gives something potential energy, what gives an object the energy required to move. Let's start with a very simple case of I have this pen and I'm going to drop it. Now, as it falls, we know from our study of forces that it's going to accelerate because it's under the influence of a gravitational field. As it accelerates, it gets faster. So how fast this pen is going to fall is going to be dependent on a few things. It's going to be dependent on how high it is above the ground, right? Because the higher it is, the faster it can go. It can accelerate for a longer distance. It's also going to depend on the acceleration due to gravity. So this is a measurement of energy. It contributes to the energy. So gravity is the thing making this thing fall. And it's also going to depend on the mass. So yeah, those are all going to be proportional. So we typically use the expression mgh, mass times acceleration due to gravity times the height, to give us our gravitational potential energy. Our kinetic energy is a little more interesting. I'm not going to derive this one for you because it's a little nasty and a little bit outside the scope of this class. But our kinetic energy, at least in all the things that we're going to be talking about, can be expressed as 1/2 the mass of the thing times the square of the velocity it's moving at. So our gravitational potential is mgh. Our kinetic energy is 1/2 mv squared. Since we know that the total energy is the sum of those two, then we can write total energy as this. One more thing we need to worry about. We need to talk about vectors. So if we think about dropping the pen from a certain height, we've got to pick an inherent up and down, right? Typically, gravity is going to be down. So we're going to have a negative vector here, a negative in front of the mgh, usually. Usually we don't write it in this expression because we understand that it's wrapped up in this g or h, whichever variable you're using to define up and down. It's got to be wrapped up in that. Well, we need to do a little critical thinking and investigation now. If the total energy is the sum of these two, let's think a little bit about a problem where we have our pen, we're about to drop it. Let's think about the total energy in the system. We'll first start and we'll calculate its gravitational potential energy, just mgh. So this is at the point that I release the pen, okay? It has not started falling yet, I've just released it. Does it have mass? Yes, of course. Is there a gravitational field? In other words, is there some acceleration here? Yes, 9.81. Regardless of where you are, it's 9.81. Height. So what does that mean? Height is not necessarily the distance above the ground. It's the distance above whatever our reference point is. So for example, if I want to measure dropping this pen from where I'm standing to the ground. So if I hold it just a little bit above my head, we're going to call that about 2 meters. And I drop this thing, I might be worried about what the velocity of the thing is when it gets to my waist, say 1.5 meters. But I might also be interested in how fast is it going when it hits the ground. So if we think about the point of release, we're talking about to some arbitrary point as our h. That's our distance. In most cases, we're going to consider the ground to be our 0. And then of course, up would be positive. So there's our h. So we have some value m, we have some value for g, we have some value for h. So we absolutely have some potential. At the point of release, however, let's take a look at the kinetic energy. 1/2, that's just a scalar, we can't do anything about that. M, the thing certainly still has mass, right? But V is dependent, right? It's dependent on time. Because remember that velocity is distance per time. Don't confuse this distance with this height. This height is our height above the ground at some point, right? This distance is the amount of this height that the thing has traveled. So in this case, at the point we release this, we have not changed our distance. So this is really more like delta t or delta d over t, which looks more like a velocity vector, right? Well, if we have not changed our position yet, then our delta d is 0. So 0 divided by t gives us 0, which gives us 0 velocity, which means kinetic energy goes to 0. So that means at the point of release, our total energy is mgh plus 0. So our total energy must be the gravitational potential energy. That is the only place this system gets energy from when the pin is falling. Conversely, at the point where it impacts the ground, H would go to 0. So that means there is no potential. All of the energy has been converted into kinetic. When we hit the ground, we're going at some velocity 1/2 mv squared. So if we start accounting for signs, what you'll find is that generally energy is going to be conserved, right? So the sum of all this energy, sum of kinetic and potential, has got to be 0, typically. Think about, let's look at the roller coaster problem. So we have a roller coaster track, and we have the roller coaster car at the top of the track. It's got some weight because it has a mass. We're going to measure from the top of the hill to the lowest point on the track is going to be our H. And we're going to have some hump here in the middle. And we're going to call that H1. Actually, you know what? Yeah, we'll call this H0. We'll call this H1. If you do any kind of programming, you're going to be used to this kind of starting place being 0. And in programming, we do arrays. We usually start counting from 0 instead of 1. Doesn't matter. It's just a convention. So if we look at the energy of the system, at the very top of the hill, we're not moving, right? The chain's taking the thing up the hill, and we've got some amount of energy, and it's all going to be potential. So the total energy of the system is potential plus kinetic. We know that at this point, there is no kinetic, so that the total energy of the system is just mgh. Or if we recognize that mass times gravity is weight, it's just weight times the height. If you want to do it that way, it doesn't matter. That's all the energy that's in the system. What about the bottom of the hill? We might want to know how fast the car is going at the bottom of the hill. Well, at the bottom of the hill, since E total is U plus K, since H goes to 0, U goes to 0, K is just 1/2 mv squared. So if we want to find the velocity of the car at the bottom of the hill, since the total energy in the system does not change, right? This is all the energy that's available to us. Since the total energy does not change, E sub t is still E sub t, then we can say that at the bottom of the hill, potential energy is E sub t here has got to be equal to 1/2 mv squared, which is all our kinetic energy at the bottom of the hill. An interesting thing happens here. The masses cancel. And we get something that looks like GH equals 1/2 v squared, or GH equal v squared over 2. We can do a little bit of algebra here, and we can say that v is root 2gh. So that's our velocity at the bottom of the hill. That's as fast as we can go, right? Because there's no more energy. What about at H1 though? Well, at H1, something else is going on. So this is at H0. At H1 though, we got to do it a little bit different, but not too much. We want to know what is the velocity at H1. We know it's a function of the amount of energy in the system. Well, how much energy is in the system? It's the total energy. Now, it's either going to be mgh or it's going to be 1/2 mv squared. I don't know what the velocity is though, right? That's the point. That's what I'm trying to find. But I know that all of the energy I put into the system just comes from gravitational potential, mgh. So we start from our E total again. And we know that's U plus K. Well, if our total energy here is mgh, it should be h naught, really. I want to keep my conventions correct. And this is also h naught. So our energy total then must be mgh naught. But now I want to find out what's going on here. This is H1. So how much potential is in the system at H1? The mass hasn't changed. Nobody's come flying out of the car. No parts have fallen off. The acceleration due to gravity has not changed. Acceleration due to gravity is still 9.81 meters per second squared, anywhere along this. But our height has changed. Now we're at H1. So notice H naught and H1 are different. Plus, our kinetic energy is 1/2, that doesn't change. The mass doesn't change. The velocity does change. That's what we're trying to find. Now we can do something interesting. The masses can still go away, but now we get something that looks like GH naught equals GH1 plus 1/2 v squared. You can work the algebra and solve for v from there. What you'll find is that v, in this case, is going to be something less than v at the bottom of the hill. That makes sense, right? We're going to start with a certain amount of energy at the top of the hill. That's all we've got. We're going to expend that energy until we get to the bottom. There's no more energy left. So all of the potential has been converted into kinetic at that point. And then as we start going back up the hill, we're going to trade kinetic for potential. Well, the only way we can do that is by decreasing our velocity and increasing our height. So as we start going up the hill, the roller coaster gets slow again. Now we know from the example here, just really by looking at the diagram, if we assume this is relatively to scale, If we look at this diagram, we'll find that as long as H1 is not higher than H naught, then this roller coaster will get over the hill. But what if H1 is higher than H naught? Well, we're going to find out that the roller coaster can't make it over the hill. Why? Well, if you do the math, if you work these calculations, you can just plug in some arbitrary numbers if you feel like playing with this. What you'll find if you put the new H value, say some H2 way up here, and you plug it into this total energy, what you're going to find, if H2 is greater than H naught, then the energy equation doesn't balance. You get more energy out than you put in. That's called perpetual motion and perpetual energy, and it violates all kinds of laws of physics. So probably don't do that. Don't tear a hole in the fabric of space-time, please. So we know that we have to balance the energies. Now, using this, remember, back like the first week of class, first lecture or something that I did, we talked about, I have a baseball or something and I drop it off the top of a building. And I wanted to know how fast the thing was going after a certain amount of time. Well, remember how we did that is we had to use our kinematics equations. Right, our position, our velocity just ended up being v naught plus at, and our acceleration is an acceleration. And we also know that velocity is distance over time and acceleration is velocity over time. And so we took the baseball, we dropped it off the building, and we had to play with vectors, right? And figure out, okay, what does the acceleration do to gravity? It's 9.81. And so that means that it's accelerating. So that's going to be 9.81 meters per second squared is going to equal to the velocity of the object per the amount of time it's traveling. And if we want to know after a certain number of seconds how fast the thing is going, then we just did a times t. And that gave us our velocity, which is interesting because we typically assume v naught to be 0. But if we tried to do this problem again, and we said, now I take the baseball and I throw it straight up in the air, and it goes to some height and comes back down, then we had to start playing with, okay, well, first of all, I got to figure out how long it takes to get to the top of the arc. And I did that by recognizing something that we've been using in energy, that when the thing gets to the top of the arc, it stops because it has to turn around. We can now do the same problem with energy, though. Think about this. So now I'm on top of the building with my baseball, and I want to know, say, how fast the ball's going when it gets to the ground. Well, what if my building is some height h? I throw the baseball up with some velocity, and then it turns around and it hits the ground. The energy method is real easy now, right? Because I can say, okay, how much energy does the ball have when I release it? It's not the gravitational potential energy, because that's not what's causing the thing to move, right? What's causing it to move is me throwing it in the air. So all the energy it has is whatever kinetic energy I've given it. So I know the mass of the thing, and let's say I throw the ball at 5 meters per second. Now I know the velocity, right? So I know how much kinetic energy there is. I know the total energy in the system. Then I know when it gets to the top, that's going to give me some gravitational potential, right? But the gravitational potential, if we want to know the velocity at the bottom, has got to be mgh plus, we'll call this distance L. So then our potential energy is H plus L, right? L is going to be dependent on how hard I threw the ball. Since I know that, and I know all of it is converted to 1/2 mv squared at the bottom, then I set my new potential energy, mgh plus L, equal to 1/2 mv squared. M's go away. I calculate for velocity, and I know the velocity when it hit the ground. And if I know velocity is distance over time, and I know these distances, then I can easily plug it into my velocity equation and find the time. Very, very simple. I told you this was going to piss you off when you learn how to do the energy method, because the energy method is so much easier and so much cleaner. It is also much, much easier to do with energy when you start talking about things like air resistance. Because when you start talking about air resistance, if you start talking about things like rotational inertia, then these equations get pretty nasty. But energy is going to remain the same. In fact, we know energy remains the same, so much so that we have a law that we use in physics called the law of conservation of energy, right? You cannot add or remove energy from a system. Now that energy might get transferred, it might get converted to something else, right? It might be heat, it might be light, it might be sound. But the total amount of energy is not going anywhere. That's going to remain constant. So we can do these kind of energy problems very, very easily. I think that's where I'm going to stop for today. And I will continue on with this Wednesday at our lecture. As I said, I will have the second test posted up for you on Tuesday morning. So be on the lookout for that. Again, it will cover just our two-dimensional force inclined plane problems and our uniform circular motion problems. And you'll have a few days to work on it, and then you can go enjoy your spring break. As always, if you have questions, you'll find me. Yeah, go ahead, Star.
Oh no, thank you.
Yeah.
Yeah. Energy is easier.
Yeah.